Hi, and welcome everybody to this online course on energy trading, portfolio management, and risk management. You could also call it energy management. My name is Felix Müskens, and I will be teaching this course. First, some on my background. I am Professor of Energy Economics at Brandenburg University of Technology. You find information on our webpage. I have experience in the subject I'm teaching here from both research and publications in the field, from working in this area, heading the portfolio management team at Trianel European Energy Trading some years back, also from consulting companies on the implementation of these activities, and I am the elected scientific member of the European Energy Exchange's Exchange Council. So in short, I have an extensive background on the subject of energy trading, portfolio and risk management. Let's see what I would like to teach in this course. We start with an introduction, an overview, very brief, generation, utility, wholesale markets, retail markets. In particular, we will discuss what we will cover in this class. Then also very briefly, and I assume that the viewer is familiar with some of these concepts, the characteristics of energy commodities, the merit order, and price formation on energy spot markets. Then we have two main areas, two main subjects, you could say. The first is energy trading and portfolio management. We start this area with prop trading on wholesale markets. So how do you earn money if you don't have any assets or final customers? You just trade on the wholesale market, you buy and sell on the wholesale market, and you try to achieve revenues doing that. Then we will analyze the retail side. We will focus on an energy utility with the retail business. And then we will look at an energy utility with generation assets only. So assume you, for example, own a power plant and sell the energy produced, the electricity produced by this power plant on the wholesale market. That's the third subject in this portfolio management topic. And then, last but not least, subtopic 4, integrated portfolio management. So here we assume, for example, a large municipality or an integrated energy company has generation assets, buys and sells energy on the wholesale market, and last but not least, also delivers to final consumers. So that's the portfolio management element. The second major element is risk management. We will start that with types of risk most relevant for the energy industry. Then we will discuss credit risk. Then we will discuss price risk. These two are the major risks for energy management, for energy trading. Obviously, price risk is essential. Credit risk is sometimes overlooked, but I can't stress the importance of credit risk enough. Companies have gone bankrupt over credit risk. So this always has to be borne in mind. And then we finish the class with risk management processes. So what should you do within a company, within a utility, for example, to set up perfect or at least appropriate risk management processes? That's the outline. Let's immediately start with the introduction. This slide here shows what we will cover. So we can have generation assets, for example, for electricity, as I said, power plants, conventional or also renewables, could be a wind farm, could also be even a gas field. If you, for example, operate a gas production facility, that could also be covered here, or that will also be covered here as a generation asset. Then in the middle and the center of the slide, we have portfolio management, which is an operative function, which can be a separate unit, can be in the same unit, it can be in different companies. We will analyze that. But the portfolio management here in this sense takes the generation, the generated electricity from the generation assets, and sells it. And the portfolio management also decides on how to operate the facility, the generation asset. Then at the bottom of the slide, you see the wholesale market, which also integrates with the portfolio management. Portfolio management may both sell energy, gas and electricity mostly, on the wholesale market. It may also buy gas or electricity or any other energy commodity from the wholesale market. And last but not least, we have a fourth arrow from the portfolio management to the retail market. Retail customers, such as households, businesses, industry customers, final customers typically, buy electricity from companies, and the portfolio management unit can help to manage this process. So that's the whole integrated word. If you do all this, then it's an integrated portfolio. However, we keep things very simple and build on it step by step. So the first thing we will analyze is just the center of the slide, the portfolio management and the wholesale market. This is what we call prop trading or proprietary trading. So a company can be a bank, can be a commodity trading house, can be a hedge fund, trades at its own risk and reward. So the portfolio management here is trying to, one must say, make money by buying and selling on the wholesale market. There is no generation in the background, there is no retail customers, no final consumption on the other end. So we just buy and sell before the energy gets delivered, and we want to make a margin, a revenue, a profit with those activities. So that's the starting point. Next point is focus on retail business and final consumers, as we said. That does not only involve the wholesale market, so that's kind of the next step in terms of explaining the procedure. Here we also again keep it simple. We assume the portfolio management, the utility, the energy manager, as a person buys on the wholesale market, and then your company sells to retail customers, sells on the retail market. This is typical for municipalities, for example. A typical municipality, Stadtwerk, buys energy, both gas and electricity, and sells it to final consumers like households, but also other customers, businesses, industry customers, mostly in the area where its delivery is historically rooted, but it may also try to serve customers also outside this core region. So this aspect here, portfolio management buys on the wholesale market and sells to retail markets. You see here the blue box also. What's the activity here? It's typically found in municipalities, but also found in retail energy companies or even in larger energy companies. What's noteworthy is the same story from what all we explain here is also valid for very large energy consumers. For example, a company like Deutsche Bahn. they consume a lot of electricity to operate their trains. They are not in it to buy and sell on the wholesale market, but they have a portfolio management team with DB, which buys energy on the wholesale market just for using it within Deutsche Bahn. So they're not delivering to any other retail customers, but they are just buying their own large consumption efficiently on the wholesale market. Something very similar can be true for large, for example, chemical industry companies. They also have their own portfolio management. If you consume gigawatt hours per year or even terawatt hours per year of electricity and gas, then quite often you have your own portfolio management team. So that would be exactly the same what we have on this slide. It's just that the portfolio management team is not in a municipality, but it's directly with the final consumer. So essentially the task of the portfolio management team is to optimally procure the energy which is consumed by the production processes of that specific company. So this is also what we will cover in that area. Then we move on and explain generation. Here we assume that a single generation asset, mostly, for example, as I said, a conventional power plant or a wind farm, generates energy, electricity. The portfolio management team, as I said before, takes this energy and sells it on the wholesale market, and it also determines when and how to operate the generation asset, because that depends. We don't want to operate our generation asset 24/7. Usually we want to operate, when do we want to operate a generation asset? Well, when the revenue is above production costs, short-term revenue above variable production costs. And that implies what you do essentially, for example, in a gas-fired power station, you convert natural gas and CO2 emission allowances, which you need in many markets to produce the electricity. You convert that by producing electricity and sell the electricity. So your revenue is coming from the wholesale electricity market, and you buy for this generation asset natural gas and European emission allowances. So that's what's going to be covered here, and this is relevant for independent energy producers, for example, merchant power plants, for example, wind farms, for example, large solar projects, for example, also, and again, changing the commodity, gas producers. If you operate, for example, even in the United States, a shale gas field, somewhere in the Midwest, you can use what we teach here, if you don't already know, to see how you should operate that gas field, how you can sell your produced natural gas on the wholesale market, what's an optimal production schedule, and so on and so forth. Okay, and last but not least, as I said, we analyze the integrated portfolio. This, of course, also happened that you have integrated energy companies, such as, for example, large municipalities. Just one example from Germany, Stadtwerke München, Stadtwerke Munich. They have their own generation assets, they have their own retail customers, but they also access and trade on the wholesale market, buying and selling electricity. So this is the integrated portfolio, which we then in detail analyze on what happens there. Even though we have mostly covered everything, we start with the wholesale market only, then we improve and include retail, then we look at generation, and if we combine everything, we have an integrated portfolio. So as I said, this is relevant for large municipalities. This is relevant for Tier 1 energy companies like Vattenfall, EDF, companies like that. And it's also, again, relevant for very large industrial consumers. Lots of chemical companies have their own generation. Again, Deutsche Bahn, they operate their own power plants. So they also are truly integrated in the end. They produce energy, they consume energy, and they trade, again, buying and selling on the wholesale market. So it's not only municipalities for whom this is relevant, it's a much broader scale, starting actually, or maybe even going up to investment banks. If they trade commodities for their own book, what we do here is relevant. And then going to municipalities, just buying on the wholesale market, selling to a fixed customer base. That's also covered. Then, as I said, we cover electricity and natural gas in the specifics of the course. But what we say is also relevant, can even be relevant for example, oil. So it's not specific to electricity, even though we probably most often use electricity examples, but still it's all highly relevant for other energy commodities as well. However, at the background is always the limited storability. So that's probably energy commodities such as electricity, natural gas and oil, but it's probably less relevant for other agricultural commodities, for example. So we will focus this course on energy commodities. That is the outline. So that's for whom it's relevant and where you can work if you watch this class and go out, or maybe if you have already started working but would like to see how to fill the gap on what you're supposed to do in the portfolio management, you can all see this here in this online class. Okay, as I said, very brief introduction, characteristics of energy commodities, the merit order and price formation. But this is mostly a repetition. The viewer should be aware of this. There is, if you don't have anything on this, shoot me an email. I can even recommend other video classes on the foundation you need here. So, a repetition of the characteristics of the energy commodities dealt with in this course. They are typically grid bound. Electricity needs a grid to transport, natural gas needs a grid to transport. Supply has to equal demand in real time to guarantee a stable frequency or to guarantee that houses, in terms of natural gas, remain heated. So a supply interruption would be non-desirable. It happens occasionally, luckily in most industrialized countries, rarely. So in general, supply has to equal demand in real time. And the energy commodities are difficult and or costly to store. And then we have seasonality and uncertainty on supply and demand side. With seasonality, I mean that, for example, load follows a profile. Typically, a household load is low during the night because we are mostly sleeping during the night, and the aggregate of household demand is very low during the night. And then during the day, when the households wake up and economic activity starts, demand is higher. This also holds for the economy as a whole, typically. So this is what we refer to as seasonality. During the night, demand is lower than during the day. Typically, during working days, demand is higher than during weekdays, than during weekends. And then we have a difference depending on from where you're watching and for which market you find this relevant. We have winter peaking countries, such as Germany, where we typically find the highest energy demand, both electricity and gas, during the winter month, because it's cold, it's dark, people turn on the lights, people heat with electricity, people consume more gas to heat. While in the summer month, electricity demand is slightly lower, and natural gas demand by private sector goes down to very low levels during the summer, of course, because there's hardly any heating. And then in contrast, we have also summer peaking countries, especially for electricity. For example, California, Gulf region, Northern Africa. These countries all are summer peaking due to the heat you observe there and the air conditioning you operate. So the energy consumed for cooling is higher than the energy which is needed for heating, and thus highest energy demands, in particular highest electricity demand, happens during the summer month. But this in turn is just another seasonality. This is pretty straightforward to predict. You know, in summer in California, electricity demand is going to be higher than in winter, and you can predict that with reasonable accuracy, or you know the expectation, the expected value for demand is higher in summer than in winter. So that's seasonality. But then we have also uncertainty, which is the variance, if you want. So that's what we cannot forecast. For example, a week from now, on Thursday at 2 p.m., the wind may be blowing or the wind may not be blowing. This is stochastic. Or it may be warm or cold, so people may turn on the radiators or not. Hard to predict right now. So this is uncertainty. And we nowadays have both the seasonality on the supply and on the demand side, and the uncertainty on the supply and the demand side. Seasonality on the demand side, I've already explained. Seasonality on the supply side is, for example, that obviously photovoltaic feed-in follows strong seasonality. No photovoltaic generation during the night, lots of photovoltaic generation during the day. That's typical seasonality for generation for photovoltaics. And the uncertainty we have already said for the supply side. Wind may blow, wind may not blow, depending on what the weather is. And on the demand side, you have the same thing as we said. If it's truly hot, air conditioning will kick in or not. And we have an expectation for how hot it's going to be next week, next month, but we don't know for certain. There is always some variance, some uncertainty in there as well. So that's another characteristics here, which of course makes supply has to equal demand in real time more difficult. They both change, they both are uncertain. Some consequences. The size of the market area depends on grid usage. So, for example, Germany and France may be an integrated market area with identical prices during some hours. During other hours, they may not be. If the interconnector is a binding limitation, they have different prices. So, for example, assume Germany has a very high price or France has a very low price. Then, of course, actors in French energy trading companies in France want to export electricity to Germany. And then we fill up the interconnector, but at some point the interconnector is, let's assume that is filled to the max. The interconnector constraint is binding. And if we still have higher prices in Germany, well, then we can't export anymore from France to Germany, or Germany cannot import anymore. And then we have different prices, different markets. While if we just have a few megawatts flowing between these countries, and that's already enough to nivellate, to equate the price levels, then they have the same price, then they are one large market. So in terms of markets, this is important. Maybe even more important is the last point on this slide. Electricity today, meaning if we consume it today, is a different product compared to consuming electricity tomorrow, next week, next month. And the prices vary greatly, mostly coming from the seasonality and the uncertainty. For example, if demand for electricity is low during the night, prices will be low during the night. When demand is high during the day, that will often translate into higher prices. However, we will discuss that later on, whether it's still true in modern electricity systems. Same, of course, for natural gas. Natural gas for delivery today is a different product compared to natural gas delivered next Sunday or in the summer. During the peak of the summer, we said natural gas demand is low on the northern hemisphere because we heat much less. We essentially just use natural gas in Germany for warm water purposes and for industrial purposes, but not for heating rooms. And thus, price for natural gas in the summer is much lower. So this really translates into different prices depending on the time of delivery, the time of consumption. So this is a very important fact to remember straight away. Electricity today is a different product compared to electricity tomorrow. They have different prices because supply and demand vary over time. And the intersection which drives the price shifts. Okay, so this, if you're not aware of it and you want to follow this class, you should take a few minutes to repeat. In particular, the merit order theory I find extremely helpful to close the gap and understand how price formation for energy commodities works. Here, just as a repetition, you briefly see that you have the supply curve, sorted supply in ascending order, and you have demand levels, and the intersection of supply and demand gives the price, but that's for the viewer to repeat. Interestingly, this picture is similarly shown at the European Energy Exchange. So the exchange explains with supply and demand how price formation on the exchange works. And to an economist, this warms my heart that you find what the economist explains in its simplest models, Economics 101, Microeconomics 101, markets intersecting supply and demand, made it on a website of a power exchange. That's just great to know. And you also see as the viewer how much in line with reality, with what you actually need, what we are doing here is going to be. And I can promise I often received feedback from former students saying that they indeed in particular used and practiced what they learned in this class. That is the introduction. Thank you very much for watching it.